Thank you everyone for coming to the first coastal RSR session this year, and we are very excited to have these sessions again this year for coastal research. Today's topic is about recent advances in assessing coastal compound flood hazards, and today's speaker is Dr. Tim Leijnse. Uh, Tim completed his PhD in 2025 at the Institute for Environmental Studies at University of Amsterdam, and his research was improving larger scale coastal flood risk assessments by incorporating wave-driven processes. He's a coastal engineer and researcher at Deltares in Delft, the Netherlands, where he has been working since 2018. His work recently centers on compound flooding during extreme events, including storm surge and tropical cyclones and wave-driven flooding. Tim has contributed to a range of international projects, including some in the US. He has extensive experience with coastal modeling tools such as SFINX, TCWise, Delft 3D, Swan, and XBeach, and currently serves as the product owner of SFINX at Deltares. Today, Tim will be sharing his work on recent advances in assessing coastal hazards. So with that being said, please join me in welcoming Tim Leijnse. Tim, the floor is yours.
All right. Thank you so much for the invite. Happy to talk to you, calling from Delft in the Netherlands. Very nice to be invited to this talk. Let me see whether I can get this sharing to work. Well, let's see. I think the screen should be coming up. Is that correct? Perfect. Well, I don't have to introduce myself anymore after this excellent introduction. I will talk what we've been working on for the last couple of years, partly as part of my PhD and also together at just projects at Deltares, which is an applied research institute here in the Netherlands. And I've done this, of course, together with a lot of colleagues here as well. Well, let's see. Starts working. Yes. So, as many of you probably are aware, extreme events impact hundreds of millions of people in coastal areas and other floodplains worldwide. So as you can see on the picture, large-scale flooding events and also in riverine areas can have big impacts on coastal communities, from flood damage to forced displacements and deaths. And climate change and population growth in coastal zones will increase flood risk even further. Well, what can we do about this? We'd like to give coastal managers as accurate and actionable information about flood hazards as possible, so that they can take measures to reduce flood risk. This can be through protective measures and early warning systems, ideally so that people in pictures don't have to put sandbags in front of their individual houses, but know in advance something is happening or are better protected in general. And we'd like to not only do this on a small city scale, but do this at large county or statewide scales, and thereby account for a lot of different uncertainties and different flood drivers or impacts of different types of extreme events. Well, the complication hereby is that flooding can come from different directions. So even though we're looking mainly at the coast, where flood drivers can come from tides, storm surges, waves, there can be local wind setup, but at the same time, especially in these low-lying vulnerable deltas and estuaries, there can also be a lot of local rainfall adding to flooding issues. There can be a lot of rainfall coming from upstream through the rivers. So there are different types of flood drivers. And as you can imagine, it is uncertain whether those different flood drivers will happen at the same time. They might be related. It's, for instance, a hurricane making landfall, then the rainfall is somewhat related, but it can also be that the rainfall is falling further inland and then a discharge peak is coming from the watershed, but it might be with a different timing than the storm surge. But in a system or setup, they can also happen at the same time, and then it can happen that they amplify each other. So then you have the so-called compound flooding, so that Could be that the water level of the coast is already high due to a storm surge, and with local rainfall or riverine flood drivers bringing water down at the same time, the water has no place to go. And this can happen here, for instance, this is in Charleston on the East Coast, where that can happen, and especially the area where these flood drivers come together is where relatively low-lying, a lot of urbanized areas are present. So therefore, if we want to look at this flood risk, we should really take into account these compound flood drivers. Well, we can predict this in different ways with computer software. So with numerical models, in general, we have sort of a balance between speed and accuracy. And traditionally, sort of two methods have been used for this. So either simple or too simple, but very fast methods. So the bathtub model, where you just look at, oh, this is maybe my predicted maximum total water level of the coast. You look at your DM, you take a horizontal plane, and you assume everything below is flooded, everything above it is dry, which is very fast. But as you can imagine, you cannot take into account all these different compound flood drivers and whether there's timing involved or coastal protection. So these are generally too simple. On the other hand, you have accurate but slower models. Generally, I call them advanced models, which are very accurate. Can be models like RSR, Deltares, Mike, models like that, but they also generally come at a computational expense. So generally, I show sort of like this type of figure. So there's some sort of disbalance. The exact line is, of course, arbitrary, but the bathtub type of simple models, or for riverine models, you have the hand method. They're more on the left side, so not as accurate, but very fast. All the way on the right, you have all these advanced models, but there's sort of like this area in between that we would like to cover with models that we now call like reduced complexity models. So these are generally the models like Sphinx, where we sort of try to make the model still accurate, still resolve physics, but make them a lot faster. And so far, we've been aiming for like 100 times faster than the advanced models, and ideally not lose a lot of accuracy, of course. So sort of the general goal of my research so far is sort of developing new methods to provide better insight into coastal flood hazards from extreme weather. Well, this is a slide from my PhD defense, but sort of the general topics that I'm working on is large scale with resolving probabilistic coastal compound and flood modeling. And I'll have a couple of slides on most of those different aspects. So the first part is on the flood modeling. So we introduced a new dynamic fast open source numerical model called Sphinx. It was started already in 2017, a long time ago, by my colleague Maarten van Ormond. And so the starting point was trying to make this model that's a lot faster, but still is a dynamics numerical model, still resolves physics. The starting point for this was a method developed by Bates et al. 2010, which is in the list flood model, which is more aimed for riverine flooding. So we took those equations as a start and then recoded everything. And mainly focused for these coastal compound flood processes, we realized that we're missing processes like wind, atmospheric pressure, importantly waves that we wanted to include. And while doing this, we also saw that like the original equations were slightly too reduced, so we needed this affection term to be able to get wave run-up added in there correctly. So we added it as well, but you have a switch that you can turn it on and off. And we presented it about five years ago. It became open source, and we have so far had a very nice uptake by both the scientific community and also practitioners. And because the model is open source and open access, people can just download it and start use it. So it's been very nice to see a lot of applications all over the world. I think I haven't covered all of the applications, but these are the ones that we know of in blue. I, of course, want to try to cover the whole map. We're working on it. Well, in terms of flood modeling, we have showed when we had the Sphinx introduction paper that we can predict accurate results in real life cases. So we had this example that we started doing in Jacksonville, Florida during Hurricane Irma 2017. There was both on the coast quite a significant storm surge. And at the same time, the hurricane also brought down quite a lot of rain. There's also a riverine area sort of behind the city of Jacksonville, where actually also like a lot of water was pushed up. There was a combination of rainfalls. It was a real compound flooding event. And we modeled this both with the advanced but more traditional Delta3D flow model, and also with the versions of Sphinx with and without advection. And in the figure, it's condensed. It's only one of the observation stations from USGS that we're showing here. But this is sort of in the riverine area near the city of Charleston itself. And in black, you have the observations. And then the green line is the one from Delta3D. And the blue and the red ones are the results from Sphinx. So you can see especially the peak water levels are very close to each other. Nowadays, we would cover the observations better because we have also subgrid approach and other new additions. But back then, this was already a very nice result, especially since the computation went down from 40 hours for Delta3D on my laptop to only 15 minutes. So that was a very big speed up, while the results were like, well, very comparable. So it was a very nice result. And therefore, well, as I said, we are looking at coastal compound flooding. So what we can then also do, because our model is still the dynamic model, has all these processes in there, you can start playing what if games. So you can say, like, if I have all the drivers, but I turn off the wind, what happens then? Or if I turn off the rain or turn off the surge and the tide. So you can also make these into few different simulations. So the blue was what Sphinx predicted with all the drivers turned on. It's a bit more inland, so the difference with the surge is still like half a meter or so, but it's not the only important driver there. So it's not only the surge and the tide. In this case, having no rain also led to quite a lot of difference between the yellow and the blue line. But even wind, a bit more unexpected because it's sort of relatively inland, but it's a very large estuary, and the wind was pushing exactly in the direction of the estuary. Also, the wind had a significant contribution there. And with Sphinx, we could capture these different processes. And also the redlift drivers also depend in space. So closer to the coast, of course, the storm surge is more important, and more inland, completely inland, is mostly the rainfall and the pluvial. And you have this compound flood zone where sort of all of them are sort of important. So ideally, you just take all of them into account. And thereby, well, it's not in these slides, but then we also showed that with the bottom model, in some areas you have a large overestimation, some areas you have a large underestimation. And then we showed with relatively limited computational spend, you can improve a lot compared to the bathtub models. Well, if we go to the next part, that is the wave resolving part. So far in that case of Jacksonville, we didn't include waves yet. But as we know, waves can also have a big impact, especially directly at the coastline. But often they're not included in flood models, or especially not if you do larger scale, hundreds of kilometers of coast flood predictions, because wave physics are complex. Generally, you need high accuracy, high resolution in your models, and then it takes a lot of time. Therefore, they're generally not considered. Or only in a simplified way using like the estimates like Stockton for the wave setup, something like this. But at the same time, you can have flooding events like this. This is in the Philippines. This is a village that's normally protected behind a coral reef. And during Hurricane Haiyan in 2013, there was this massive 16-meter significant wave heights offshore. And this created like this incredibly almost like 2-meter, well, these are infragravity waves, but it's almost like mini tsunamis almost that wiped away the whole village. And in this case, the storm surge was only 60 centimeters. There was sort of in the region a storm surge warning system, but nothing was triggered. But at the same time, these giant waves wiped away all these houses. So actually, for my colleague Martin, this was sort of the reason that he wanted to start developing the Sphinx model, because of this case, because he saw, okay, we need something that is faster, but he couldn't do it with L30 at the time. Well, we have showed in some of our papers that we can now actually reproduce this with Sphinx. So this is just a quick video of the modeling just in that area on the coral reef. Sort of the green dot is sort of where that house was, where the video was taken from. You can then model this also with the waves included in the Sphinx model. And Sphinx itself here runs very fast. It's like a minute or so. But in this case, we still forced it with XSpeech. So like one of the more advanced, high resolution, but slower models that still took like 3 hours or so to run. So the positive side was that the flooding part went very quick. We were still relying on a slower wave model to get the input for Sphinx. So then, well, we could show that we did it well compared to XSpeech. So XSpeech was sort of the black line, and then the blue and the red is again Sphinx. And then especially the red one, which is Sphinx including advection, is very close to the XSpeech result, which is very good. But as I said, we still needed to run XSpeech. So then through some other research, then the question was like, okay, how do we overcome this step and in between that we don't need to run this computationally expensive model? So some of my other colleagues, including Dana Ulvink, who started the SnapWave model, who is also the founder of the XSpeech model. He started working on a new fast implicit wave transformation model to translate waves from offshore to nearshore just in a matter of seconds. It's a wave spectral model, so it's a bit similar as a model like Swan or WaveWatch, which you might know, but it has some simplifications in there. So it's actually more similar to an old school Hiswa model. But then he made it onto an unstructured grid, and that it's easily to integrate in models like Delta3D, Flexible Mesh, and Sphinx. So this is to estimate the short waves in a large area in a quick way. And on top of that, in the end, what we want to know for Sphinx is what are the infragravity waves. So we started then including also infragravity waves in SnapWave. So it's a wave spectral model, so you solve sort of a wave energy balance. So what we've done is add that to SnapWave. So now we're not only solving the short wave energy balance, but now also the same for the infragravity wave balance. But there's sort of this linking term in between them, that the closer you go to the coast, waves start to show and develop, and then some energy is transferred from the short waves to the long waves through bound shoaling. So we are adding a term for that as well. To keep computational costs down, we sort of simplified this based on theory. So we didn't need to resolve the individual water level in there as well. So in the end, it's sort of related to some sort of shoaling factor and the energy in the infragravity waves, and sort of the gradient of the radiation stress. So it says something about what the incident waves are doing in terms of shoaling or breaking. And this alpha, sort of this parameterized shoaling parameter, we based on a lot of XSpeech simulations for a lot of different slopes and wave conditions. And there's sort of data fitted through there. So it's sort of a partly physics-based, partly parameterized approach. But what we could show with this is, for instance, compared to field validation data from the LIDA-DOC from already 1990s, from a measurement campaign, is that from going from offshore on the left towards the coast on the right, you can model in blue what the incident waves, the short waves are doing. In yellow, you can model what the infragravity waves, how they slowly start to increase towards the coast. And sort of match the observations quite nicely. So it was a good indication that the model produces something realistic, even though it's a bit more reduced complexity. And with the nice thing is that we could show is then, because sort of both SnapWave and this approach is faster, is that you then could estimate incoming infragravity wave heights at these large scales. So this is around the Outer Banks in the Carolinas, so a couple of 300 kilometers of coastline or something like that. And you could then estimate that based on the bed level and the offshore wave conditions, you could then quickly estimate what the short waves are in the whole area. And after that, on the right, plot also the infragravity waves. If you would do this type of scale on an XSpeech model everywhere, then you would be computing for days. So that's very nice, especially if you want to go to quick early warning types of assessments or probabilistic flood risk assessments. And it's very nice that you can sort of estimate a good idea of what the infragravity wave height is near shore quickly. So afterwards, we have sort of integrated this snap wave and gravity part into Sphinx, so they're part of the same code base. And then for the short waves, this is what snap wave calculates, and these are coupled into Sphinx through wave forces, and that can lead to a short wave in the setup. So that is what typically an SRC Swan or Delta3D flow wave model is also solving. And then what we do additionally is that we then also calculate this instant gravity wave energy from deep water close to the coast. And then sort of in the braking zone, then we link this also to Sphinx through a wave maker. So we then take this infragravity wave height and the wave period, so these nearshore infragravity wave conditions, and we started sort of putting in this wave pedal that is in the Sphinx model itself. And thereby you can start to include run-up and overtopping. And this is integrated, so it's a combination that you can still have storm surge in there and rainfall and riverine flood drivers. And the last piece is that we now also implemented a quad-tree approach so that you can make the grid resolution finer locally, so that you can still keep deep water or further inland, for instance, you can keep it on a bit coarser resolution. But really at the coast where you need this higher resolution of like 20 meters or so at least to get the wave run up and the process in there, you can make it finer. Well, to show you a little bit that this works in the real world, this is an example of Hurricane Michael 2018 that hit Mexico Beach in Florida. And generally there's quite some storm surge, but there's also quite some wave heights. And you can sort of see near the coast, there are these higher frequency waves. So this is where they are generated with the wave paddle. And in that area is where there are a lot of beach houses at the town, and where the waves start sort of impact these first lines of houses. And you see also when the results come a bit further inland, the model becomes a bit blockier, a bit coarser again. This is where we de-refine then. But in this way, you can sort of have a combination of both the storm surge, the water level, the tide, and the waves. And this only takes like 1.5 minutes to run for a one-day simulation. Well, what Martin, my colleague, then nicely showed is like, if you look at the area of like high water marks captured by USGS really in the houses close to the coastline, then you underestimate the maximum water levels observed on these high water marks. But if you then include the waves in there, so then all around the coastal zone, there's just more rest because of the waves, and then you can see you get a much nicer fit compared to the observations. So it shows, like for instance, these types of assessments, these waves are important. Well, when we bring all this together, so both Sphinx, the different compound flood drivers, and the waves, Sadegh did a first test to show where we can make a really large model. So this is a model on a 1,000 kilometer scale coastline, where we include both coastal compound flood drivers, so storm surge, tide, pressure, local rainfall, riverine fluvial inflow as these waves, and then we incorporate it with snap wave and infragravity waves. And we modeled this for Hurricane Florence 2018 at the US Carolinas coastline. And we showed that it's sort of now possible to study this type of scale. So you could show, and in the end, from the simulation, you get like an idea of the maximum water depth in the entire area. And of course, it's not just flooded by waves. There's also a lot of rainfall and storm surge. But now the interesting bit was, because we account for all these processes, we could look spatially what the whole simulation, the most important flood driver. So this is from the y-axis is the whole coastline, from going from south to north. And then the different colors are different processes, like the astronomical tide, the mean sea level, the tide in blue, storm surge in yellow, and then sort of the wave setup in green, and the dynamic infragravity wave run up in red. Sort of the middle, where you see the word storm surge, that is where the hurricane made landfall near Wilmington, North Carolina. So not surprising that storm surge is the biggest, has the biggest magnitude there. And then if you go further north or south, further away from the landfall location, like a couple of 100 kilometers north or south, then the storm surge is quite low, and there the tide is a larger driver. But what I found most interesting was, like, even areas quite a couple of 100 kilometers north of where the hurricane missed landfall because it went towards the coast, and waves can be generated further away and through swell waves travel larger distances. So the impact area is larger than from stern surge. Waves are actually the most dominant driver in the sort of the couple 300-400 kilometers on the top side, and there are at some locations the total water level exceeded that of the that and the area around where the hurricane made landfall if you would ignore waves. So sort of an indication, like generally we focus mostly in the landfall location, but in theory also further north or south, depending on the track of the hurricane, waves can really be an important driver as well. So to summarize, the importance of waves in large-scale coastal flood modeling, that's sort of what we've shown in this research, and we think it's sort of the next step in assessing coastal compound flood risk and early warning systems at large scales. So they've shown how we can add more physics within a reasonable time, and we've implemented this in the open source fast flood model Sphinx, and through the integration of the SnapWave model on a quadrilateral grid, we could include both incident and infragravity waves in a nice way. This is a simulation just for fun that I always like to show us how we flood our own Sphinx model, Sphinx logo with the Sphinx model. And I've looked into time. I have 3 very short slides just for a bit of outlook, and then I'll quickly conclude. So far we've mostly showed the capabilities of this flood driver for more mild to intermediate sloping beaches. So now we're also working on showing how well, testing how well it works for steep and coral reef line coastlines. The first results look promising, but we want to look further into them, how well we're actually doing. With Sphinx, so far we started mostly working on coastal compound flooding, but more and more of our colleagues started also applying it in more riverine cases, or sometimes even more upstream where there's no coastal processes involved at all. So we presented last year a webinar with results on the modeling we did for Hurricane Helene 2024 that led for large flooding in Asheville, in North Carolina, in like sort of quite steep upper catchments. So we could also validate and show that this works also very nicely with Sphinx. The last thing is a bit more, it's related, but we're starting to see, like, can we also, to speed up Sphinx even more, can we do sort of hybrid Sphinx machine learning type of approaches where we still run Sphinx, but sort of on a bit coarser resolution, and then train it with the machine learning model so that you, based on Sphinx results with a high resolution, or this could also be a Delta3D model, then you correct maybe for some of the mistakes that you make by running on a coarser model. But this is a work in progress. I'll leave it at that. Thank you for your attention.
Thank you very much, Tim, for the fantastic talk. I really enjoyed this, all the new updates in the Sphinx, actually. So we've got 2-3 more minutes for questions. I think we have time for 1 or 2 questions. And with your permission, if you are okay, I would like to share your email with them in case they want more questions, they want to reach out. So
Sure.
any questions?
I have a quick question, if you mind.
Sure, Daniel.
Hi, Dr. Tim. I enjoyed your presentation. It was really great. I appreciate all the effort that you have done for the compound flooding aspect of natural hazard. I do have one question for you, and it's regarded about the special exchanging information and temporal exchanging information between different components of the compound flooding. For example, where do you exactly exchange the wave, tide, and storm surge information with the rain, riverine, and wind components, and how frequently these components interact with each other? I appreciate it if you can answer that. Thank you.
Yeah, thanks a lot for your question. That's a good question. So what we sort of do is, so if we make for a certain area, we make a model schematization for the Sphinx model, and it has different boundary conditions. So, for instance, from the marine side, for instance, 10 meters water depth or so, we maybe nest in other data sets or maybe a different offshore model. So we put in there the water level. That's a combination of the storm surge and the tide. You can just, in different locations, you can put it in, and that's the time series of the water level. So you sort of nest it in a different model. At the same time, well, your model, generally you don't go all the way up to the mountains, but well, at least you go maybe for like 50 kilometers or more inland, sort of the closest watershed. And at some point, you have inflow points of where rivers would enter your domain. And for instance, from a national water model or something, or observations, you also take time series, discharge time series. So you put those into the model. And for the area that covers your model, your region, you can also put in rainfall, spatially varying, for instance. So that's the rainfall that falls in your domain. And these are also time series. And those you just put on the model, and the model itself will just distribute the water due to the river and due to gravity and the momentum of the waves and the storm surge and the tide. They will just be distributed throughout the domain on whatever grid resolution you had. So within the model itself, water is just going from grid cell to grid cell based on water level gradient and momentum and things like that. So you don't have to choose in that sense where you nest. But when you make your initial model schematicization, you have to think a little bit of like, okay, where are my other data sets coming from, either from the coast or the river? So where it sort of makes sense of where I cut off my Sphinx model and sort of make a logical area. Does that answer your question?
Yes, thank you so much. I appreciate your answer.
Perfect.
Thank you so much, Dr. Tim Leijnse. We really appreciate your coming to this talk. It should be very late actually in the Netherlands. Thank you so much again. Great talk. Really enjoyed. And I encourage anyone else having questions, reach out to Dr. Leijnse. And yeah, with that being said, I would like to wrap up this session of Coastal RSR. Yeah, Robin, that's it. Thank you.
Thank you so much. And yeah,
you,
feel free to reach out, or you can Google Sphinx and try to get it running yourself, and let us know.
Thank you so much.
You're welcome. I hope you have a great day and a great weekend afterwards.
You too.
Thank you. Thank you. You too.